that's available to everybody. Okay, we are finishing up then the section on mathematical models. So there should be time today for you to ask questions or get started on that practice, because a lot of the more in-depth examples we've already gone through in this section. So we looked at specifically linear models because those are the most common. Then we jumped to polynomial models. Linear is included in that, but if it's not linear, it's a quadratic, cubic, quartic models. Those are the second most common, I would say. So polynomials in general are the most common. Today is just looking at the other types of functions that we will be using this year. So making sure, again, you can recognize from a formula or from a graph what type of function you have, and just understanding the basic characteristics of those functions is helpful. Two of the functions we're looking at today are exponential and logarithmic, and those actually have their own section as well in Chapter 1. So we are going to be looking more closely at exponential functions and logarithmic functions than what you see today. Today is just making sure you can recognize the formula and you recognize the shape of the graph. So we're starting out with power functions. The first three are actually power functions. And I didn't include this, but if you want to write in this little space up here, in general, a power function has this form: f of x equals x to the power of a, where a is a constant. Okay, so the three power functions that are listed in those first three rows are power functions with a specific type of a value. So in general, if a function has the form x to a power, it's a power function. And notice it is just one term. So if it has more than one term, then depending on the exponents, it may be considered a polynomial. So we're first going to look at if the exponent a is equal to n, where n is a positive integer. So n would not be 0, n would not be negative, n would not be a decimal or a fraction. So we have f of x equals x to the n. Because the exponent is a positive integer, this does make it a polynomial. This also fits into the polynomial family. So this would be a polynomial with only one term. So you will be identifying, or rather characterizing, functions in this section. Some of the practice just gives you functions and says next to it, determine what type or what families of functions does this equation fit into. So this would be considered a power function and a polynomial. You'd have to list both. And then in general, power functions, there's two shapes of graph that you could see. I guess you could consider it three. Lines would be grouped into this. So if you just had f of x equals x, you would have a line here. I guess I'll draw them on here. So this is kind of its own thing. If you have f of x equals x, or x to the first power, then that will have a specific graph. It's a line with a slope of 1, y-intercept of 0. But otherwise, the graphs are kind of characterized by whether or not the exponent is even or odd. So it's just that if it's odd but it's 1, it looks a little different because it's specifically a line. So then if n is even, then this means the graph will resemble the graph of y equals x squared. So that would be if you had f of x equals x squared, x to the fourth, x to the sixth, but again, just one term. So all of those graphs have the shape that the graph of x squared would have. So x squared would be a parabola specifically. When you increase the exponent, so x to the fourth, x to the sixth, the difference, or one of the differences, is that the origin, near the origin, the graph is flatter. So it starts to kind of, it steepens off to the sides, but then towards still have that similar shape. And then these would all be even functions. So we talked about even versus odd functions. If you have a power function with an even exponent, then it is an even function. So then if n is odd, these graphs resemble the graph of f of x equals x cubed. So it'd be x cubed, x to the 5th, x to the 7th. So these do not have that little hill and valley in the middle. They're flat. So if it's just x cubed, it does not, increase and then decrease for a little bit and then go back up. I guess I could draw it here. It does not do this. This would only happen if you have a polynomial that's still a cubic function but has other terms added to it that make this happen. So if it's just x cubed, it does not have that. X to the 5th, x to the 7th also would not have this happening, but again would become flatter towards the middle, towards 0. It just flattens out and then gets steeper at the ends. So just, again, this is just recognizing if you see any of these graphs, recognizing that it could be a power function where, and then you can figure out would the exponent of that function be even or odd, or would it just be linear? Questions on those? Okay. Power functions then with the exponent equal to 1 over n. So these are also called root functions, but they are in the power functions family because 1 over n is still going to be a constant. N here is still being defined as an integer, or a positive integer, I should say. So n has that same characteristic that it had above. So here's what that would look like if you had 1 over n as your exponent. You might remember this from algebra. We will be reviewing this because you will have to rewrite rational exponents as roots a lot, especially when we get to derivatives, or roots as rational exponents. I guess we go the other way more often. So remember that this is equivalent to the nth root of x. So the denominator is the index of the root of the radical, and then the exponent on the x is the numerator of that fractional exponent, rational exponent. So that is the nth root of x. So this would be like your square root, cube root, fourth root functions. And these also have special characteristics depending on whether or not the n value is even or odd. If n in this case is just 1, it would still just be x, so it would still just be linear. So that wouldn't really be considered a root function. But I'm going to split this, and we'll look first if n is even. So an example of this, just to think of this, you could think of what it would look like if we had the square root of x. And I know I did hear some of you earlier, I think last week, talking about what the graph of the square root function looks like. So if n is even, square root, fourth root, sixth root, they're all going to have that similar shape that the square root function has, starting point at 0, 0, and then kind of curving up that way, continuously increasing, but does start out steeper and then flattens out. And I'm also going to put on here, I guess I could add it up here as well. Because these are all considered polynomials, I'll just list the domain since I'm going to list the domain for the root functions. These all have a domain of all real numbers or negative to positive infinity because they are all polynomials. And we had already characterized the domain for polynomials yesterday. What is the domain for the square root function and therefore for all even root functions? 0 to infinity? Yes. 0 is included. So here the domain would be 0 with a bracket to infinity if you're writing it in interval notation, or x should be greater than or equal to 0 as an inequality. And again, keep in mind, this would be the domain. If there were any transformations happening to this that would move it somewhere else, your domain would change. But then it wouldn't be characterized as a power function if there's extra terms or extra things being added to it. So this is exactly what it looks like if it's a power function. Then if we look at odd values of n, these graphs, so this would be like cube root, fifth root, seventh root, ninth root. These all resemble what the graph of the cube root function would look like. I'm also going to put here, after n is odd, I'm going to put n greater than or equal to 3. Because again, if n was 1, it would be linear. So it wouldn't be a root function. Okay, so cube root function. Looks like this. Kind of looks like an S-ish. Okay, so if n is odd, if you have an odd root, what is that domain then? It's all real numbers, yeah. Negative to positive infinity. So just keep that in mind too. If you are taking the cube root of something, fifth root of something, you can have a negative number inside of that root. Cube root of negative 8 is negative 2. So that is all real numbers for that domain. All right, and then the last special type of power function we have up here is if the a value is specifically negative 1. So this is called the reciprocal function. So this, as a power function, would look like x to the negative first. But again, this is reviewing from algebra properties of exponents. How can you rewrite this so that the exponent is not negative? 1 over x. Okay, you will have to, these two things from algebra, just rewriting, usually we go from a root to an exponent or from a fraction like this to a negative exponent. You will do that a lot because then it makes it easier to take derivatives and such. So we'll definitely be reviewing those, how to rewrite things using algebra. So this graph, if you graphed f of x equals 1 over x, this is a hyperbola. You may remember from Algebra 2. However, it's not a hyperbola we would have ever graphed in Algebra 2 because it's a like a diagonal hyperbola, if that makes sense. So this one specifically looks like this. Has this curve in the first quadrant and then a similar curve in the third quadrant. The reason we would have never graphed ones like this, we either graphed them if they were strictly vertical hyperbolas or horizontal hyperbolas. This one, if you think of f of x as being y, I could also, so maybe I'll write this up here just so you can see it a little bit easier. I could multiply both sides by x, so a similar or rather equivalent equation would be xy equals 1. And we never graphed in Algebra 2 conic sections that had an xy term. So the xy term is what makes it tilted versus strictly vertical or horizontal. All right, and then, domain for this. Any ideas how you would characterize that domain? Just looking at its graph. All real numbers besides 0, yes. Or you could even look at this equation, x can't be 0, it's in the denominator. So I'm going to write this in interval notation. It would be negative infinity to 0 with a parentheses, 0 is not included, union 0 to positive infinity. So we can go all the way up to negative 0.00000001 or even closer than that, and then starting at positive 0.0001 and going all the way up. So you just can't include the value 0. That's an asymptote. Rational functions we have mentioned, we've talked about, so they have the formula of a form, f of x equals p of x over q of x. where both p of x and q of x have to be polynomials for it to be rational. And when we get to algebraic and look at some of those examples, you'll see why, or see what would make a function that is a fraction like this not rational. So you'll be able to tell if it's rational or if it's not rational. So rational functions are a ratio of polynomials. That's how they're defined, ratio of two polynomials. They do not have a specific type of graph. It just depends on which rational function you have. All their graphs look different. But the domain I'm going to write this in set builder notation just because without having a specific example, I can't write the interval notation. The domain would be all x values that are real, so x values that are elements of the real numbers, such that the denominator, so q of x, cannot equal 0. So all x values such that q of x is not 0. That would be a way to characterize the domain of every rational function. And as I said, all their graphs look different. And then we have below this algebraic functions. These do not have a specific formula. So how algebraic functions are defined, they are constructed using algebraic operations. And those algebraic operations include addition, subtraction, multiplication, division, and roots. So any function that is constructed using those operations is considered algebraic. So that means all polynomials would be algebraic functions. All of these power functions we just looked at would be considered algebraic functions. It does include all rational functions. Do you have a question, Connor?
I was just going to ask if that included the power functions.
Oh, yes. Yeah, it would include the power functions because, well, this is a polynomial already. This would be a root, and then this is division. So it would include all power functions and rational. Do you want to make that note? Includes all well, I'll just put this here. All of the ones we've looked at so far, it includes all polynomials, power, and rational functions. But then there are some functions that would not fit into the categories of polynomial, power, or rational, but you would consider them algebraic. So some examples of those. So over here, again, they don't have a specific type of graph. I'm just going to put some examples. One would be something like f of x equals the square root of x squared plus 1. So yes, there's a root. This wouldn't be a power function because there's more in that root besides just x, but it would be an algebraic function because we have a root. It would include exponents because exponents are just repeated multiplication. We have addition in there. So that's an algebraic function. Another one. So here's one that at first glance you might want to say it's rational, but it's not. So it's x to the fourth minus 16x squared over x plus the square root of x. Okay, that is not a rational function. Can anybody tell me why that isn't a rational function? What makes it not a rational function? You can't have a square root, but why? That the square root is the issue. That's why it's not rational, but why? If you look at how rational functions are defined, it has to be a ratio of two polynomials. You cannot have a square root in a polynomial. The reason why is if we look back up here, a square root would be a rational exponent, and for it to be a polynomial, all exponents have to be positive integers or 0. So if you see something like that, it's not rational even though it's a fraction, that would be an algebraic function. Okay, then for the last ones on here, I'm looking at trig functions. Now, yes, we will be reviewing trig as we work with trig throughout. Some things you do need to know with trig. You should know, I'd say we work with sine, cosine, and tangent the most often. We do sometimes work with their reciprocal functions, cosecant, secant, and cotangent, but not as often as you would have worked with them specifically in trig. You should be able to recognize the graphs for these three. I haven't seen that you would need to recognize the graph of the reciprocal functions on an AP question. And then we do go into looking at the derivatives and integrals with trig functions. You do need to know, and Mrs. Holber may have told you last year, you do need to know the unit circle. So I know you had to memorize that last year for trig. Like if I asked you what is sine of pi over 3, you need to know that. So we'll review that as we get to it. But remember, half of the AP test is no calculator. And you might have a question that requires you to find sine of pi over 3 on the no calculator part. So yes, you have to know the unit circle. And oh, other thing, I'm actually glad, Dan, you just said degrees. In calculus, we never work in degrees, we work in radians. In calculus, we never work in degrees. So I will show you this when we get to a section specifically just looking at the graphing calculator. I'm going to have you put your calculator in radian mode. It probably already is defaulted to radian mode. And if you never have to, don't ever change it. Because if you took the AP Calc test and your calculator was in degree mode, it only affects it if you're working with trig. But if it was in degree mode, you would get every trig question wrong. Okay, that would not be great. Because you can bet on the multiple choice answers, they will put the degree answer on there. So if your calculator's in the wrong mode, your answer will appear and it's wrong. So now I think, can somebody tell me in physics, I think you use degrees? Yeah, so if you are also in physics, you are going to have to be switching back and forth. So sorry to those of you that have defense. But I will remind you, and I'll try to remind you, like the day before the AP test, put it in radian mode and then don't touch it, don't change it. So I'm going to split this. So we can look at sine and cosine, they fit more closely together. They're very similar. Tangent is different. So sine and cosine, they both have, again, as long as there's no transformations happening, they both have the same domain and range. What's the domain for sine and cosine? Yes, okay. I heard 2 pi shouted out. That is the period. I was going to ask that too. Okay, domain. It's all real numbers. It just continues, and then so I heard the range shouted out. -1 to 1. Yeah. Now, yes, if there's transformations that affects the range. So, And then I'm just going to sketch one period of each of their graphs. So for sine of x, I'm not going to full out label my axes here. I'm just going to draw a period. Immediately, I want to ask you to see if you remember, the sines start at 0 or 1? Starts at 0. And then ends back at 0. Cosine then starts at 1 if you're just drawing one period. And some of you did ask this when you even picked up your textbooks. You noticed like the front sheet, something was ripped out. And that was, it's not the answers. There's a lot of trig stuff on that sheet. It's like a trig reference sheet. So if your book is missing that, I just want you to know I do copy that when you need it and give everybody a copy because I know a lot of your books don't have it in there. But you don't even need to know everything on that sheet. You do not have to have trig identities memorized, except you should know that sine squared plus cosine squared equals 1. So if you know that one, then you should be fine. But all the trig identities that I know, I mean, trig identities were probably huge in trig. If it's some complex trig identity, they would give it to you if you needed it. And then how is tangent of x defined? How is it related to sine and cosine?
It's the on top of each other.
It's sine over cosine, yes. Sine of x over cosine of x. Okay, so then it's, I am going to write its domain. I'm going to write it in set builder because it would be complicated to write into interval notation. It does not have all real numbers for its domain because cosine of x cannot be 0. So it's all, I'll just put all x values element of the real such that cosine of x is not 0. I'll write it that way for now. We could look further into where is cosine of x 0, but for our purposes right now, we don't need to do that. And then what's the period for tangent? It's just pi, yeah. So you may remember that tangent has a bunch of asymptotes for where cosine of x is 0. Tangent is undefined in all of those places. So even if we look at the graph of cosine, cosine of x is 0 first at pi over 2, and then again at 3 pi over 2, and then it continues every pi. So let me draw one. This is one period of tangent here, and I would have an asymptote on either side, and then you'd have another period, and so on. Okay, but just being able to recognize that or having that basic understanding of its graph is helpful. Then we get into exponential and logarithmic. And again, we have, this is section 1.5, so we'll look at exponential in more detail. Same with logarithmic, that's 1.6. Exponential functions are functions of the form f of x equals a to the x. So your variable is the exponent. A has to be greater than 0, and it's a constant. So A is a positive constant. I should say though, if A is 1, I'll actually put that with the graph. If A is 1, it's not exponential. But A is just defined to have to be a positive constant. Domain for exponential functions. I don't remember domain for exponential.
All real numbers.
Is all real numbers. Yeah. And then, again, ignoring any transformations right now. So if we just had something a to the x, what would the range be? Not all real numbers.
0.
0 to infinity. Is 0 included? No. So, and I purposely asked that before I drew the graph. So you may remember, this could look one of two ways. It could look like this, or the other way. So it could be increasing or decreasing. We could, not right now. Would you like to do that? What determines if it is, well, anyone remember, I should say, what determines if it's increasing or decreasing?
Even or odd.
Not even or odd. The A value determines it.
If the A value is greater than 1, it's increasing. If the A value is less than 1.
Yes, less than 1, but still greater than 0. Then it's decreasing. So if your A value is a fraction smaller than 1, like 1/2, 1/5, 2/3, 7/8, it would be decreasing. And then how are exponential and logarithmic functions related?
They look similar.
Okay, they look similar. Connor? They are inverse functions. So logarithmic, these are the inverse of exponential. We also will be looking more deeply at relationships with inverse functions and inverse notation. So a lot of review of functions in this chapter. So they're in this form, f of x equals log base a of x. So just a reminder, that's how you say it, log base a of x. Because they're inverse of an exponential, the same conditions for a hold true for logarithmic. A has to be a positive constant. We typically look at the values that are greater than 1 as we're looking at the inverse. So we're kind of looking at the inverse of this graph. So domain and range for logarithmic. How are domain and range between inverse functions related? It's a lot of review at once. They're flipped. So domain for logarithmic is the range for exponential. So be 0 not included to infinity. Range then is all real numbers. Okay, they're just switched. Input, output are switched. So this is typically the shape of the graph you'd see for a logarithmic function. So now up above y equals 0 was the horizontal asymptote. So for the inverse, x equals 0 is the vertical asymptote. And again, we go off of this graph when we're looking at the inverse for logarithmic. And then there are transcendental functions. So just like we kind of looked at specific types of functions and then looked at the category of algebraic, we basically have functions that are either algebraic or they're not, and if they're not, they're transcendental. So all of these functions are functions that are not algebraic. That includes all of the ones I just included above. It includes trig, exponential, and logarithmic. So I'm going to put a note here what it includes. Trig functions, I'm going to just abbreviate exponential, logarithmic. It would also include, I don't have them on here, but it would include inverse trig. We do work with inverse tangent the most, but inverse tangent and inverse sine we work with when we study derivatives, and then integrals. Those are the two derivatives for inverse that you'd have to know: inverse trig, inverse tangent, inverse sine. Okay, they don't have a specific function, type, or graph. It depends on what you have. So quickly here, I know that's just a lot of information, maybe not the most fun to categorize all that, a lot of review all at once. But you might see problems like this, where you're just given the equation or the formula and you're asked to classify each function as a power function, root function, polynomial. If it's a polynomial, state its degree. Is it rational, algebraic, trigonometric, exponential, or logarithmic? Okay, so looking at A, what type of function is A? A is exponential. What about for B? It is a power function. Anything else? It would be in the algebraic category as well. It is also a polynomial, which has a degree what?
5.
So it's a polynomial of degree 5.
If we have to put algebraic under that one, we have to put transcendental A.
We should. If you look at the, like what it listed up here, it has algebraic. It never said transcendental. But we could. It's kind of assumed that if it's not algebraic, transcendental is basically it's not algebraic. So if you don't put algebraic, I think that's where they're coming from with the directions there. What about C, h of x?
Well, that seems like radical. That's an algebraic.
Okay, it is algebraic. Is it anything else? It can't be algebraic and transcendental. Is it rational? No, it has a square root, so it's just algebraic. And then what about D?
That one's going to be
It is algebraic,
polynomial.
and it is a polynomial of degree what?
4.
Of degree 4. Is it a power function?
I don't think so. No. I don't think so.
I hear some definite no's and then some no's that don't totally sound sure. How do you know whether or not it's a power function? Yes, so if it has one term and only one term, x to a power, it's a power function. If it has more than one term, it's not a power function. It could be a polynomial depending on the exponents, otherwise it's definitely algebraic.